For the past century, human activities have been releasing large amounts of carbon dioxide and other greenhouse gases into the atmosphere, which is causing a rise in global temperatures. This change is causing a variety of weather and climate change, such as the warming of Earth's ocean. However, the Southern Ocean around Antarctica is the only body of water that has not been experiencing this pattern of warming, which has confused many researchers until recently. Scientists from the University of Washington and the Massachusetts Institute of Technology have found that ocean currents are the reason that the seawater has stayed at nearly the same temperature all these years. The climate models show that the currents around Antarctica continually pull miles-deep water up to the surface. The seawater, which may be hundreds of years old, last touched Earth's atmosphere before the Industrial Age and has never experienced fossil fuel-related climate change. How could such a simple explanation keep an entire ocean from not experiencing the effects of global warming? It can actually be explained by the Earth's natural oceanic circulation models and wind patterns. The findings of this study chiefly depends on large-scale upwelling, the process of deep, cold waters rising to the surface. Winds blowing across the ocean surface push water away from the shore. Water then rises up from beneath the surface to replace the water that was pushed away. Since upwelling is driven by surface winds, the UW and MIT researchers then studied more closely the relationship between wind and oceanic circulation. Oceanographers use the thermohaline circulation model, THC, to explain ocean currents. The model just shows the global conveyor belt of cold, dense water sinking to the bottom and warmer, less dense waters rising to the surface, creating large, nutrient-rich currents. However, temperature and salt circulation were too broad for the study. The researchers looked at a more specific aspect of the thermohaline circulation model that focuses on wind-driven circulation, meridional overturning circulation, MOC. This mouthful is essentially the same as THC, but connects the water at the pole and surface with deeper waters through upwelling processes. Another wind-driven model the researchers had to consider was the Antarctic Circumpolar Current, ACC, which flows around Antarctica in a clockwise motion due to westerly winds. The ACC is the main component of the deep and surface water circulation in the Southern Ocean, and the MOC flows through it in Antarctica, picking up deep water through upwelling and flowing back towards the North Pole. So what did they find? Using Argo floats, ships, and satellites, the researchers used these models to trace how that heat moved in the Southern Ocean. Instead of the heat moving downward towards the deep waters, the interaction between the MOC and ACC was just moving it across the ocean towards the Arctic Ocean while bringing the deep waters toward the surface. It has been noticed that the North and South poles are cooling and warming at significantly different rates. While scientists are aware of the winds that carry surface waters across the Earth, the gale-forced westerly winds have become of interest. The missing surface heat of the Antarctic waters have been noticed over several climate models, but initially labeled as churning. Churning is when the heat from the surface mixes downward due to ocean currents, thus accounting for the loss of heat. The difference in the poles cooling, however, has brought a new climate model into question. This new model includes upwelling. It is suggested that water from as far as 2 miles into the Antarctic Ocean is being pulled up to the surface. This water, as mentioned earlier, is so deep that it has not been up to the surface to experience modern global warming and is pushed north by the gale-force westerly winds. This means that cool water is rising to the surface of the Antarctic, and the warm surface water of the Antarctic are being carried north to the Arctic Ocean. This creates a cooled Antarctic and a warm Arctic. All of this suggests that global warming is not an all-around, even process that affects Earth's surface equally, but is indeed influenced by ocean and wind currents. Understanding how these currents control the extra heat trapped by greenhouse gases will help researchers better create climate models and predict the temperature of the future. Knowing that climate change has a significant impact on the planet's ecosystems, studying the changing interactions between the wind and water circulations can help us in determining trends in the essential biogeochemical processes on Earth.